When tackling wire pulls in control or fire alarm systems where splices are prohibited within junction boxes and all wiring is run through conduit, several methods can streamline the process. These methods focus on efficiently routing conductors from a central controller to various devices connected via a trunk line with multiple junction box runouts. Let's explore some effective approaches. Method 1. Sequential pulls. This method involves firstly pre-measuring and cutting conductors. Accurately measure the length of each conduit leg between junction boxes and cut the conductors to the corresponding length. Secondly, bundle conductors. Group all the conductors together according to their destination junction boxes. This ensures that each bundle contains only the wires needed for a specific location. Thirdly, pull in stages. Begin at the controller cabinet and pull the bundled conductors through the trunk line to the first junction box. At each box, unbundle and pull out only the conductors required for that specific box. Repeat this process sequentially for each subsequent junction box along the trunk line. Method 2. Continuous pull with markers. This method involves firstly marking conductors. Attach a unique identifier, such as a numbered or colored marker, to each conductor at the controller cabinet. This allows for easy identification throughout the pulling process. Secondly, pull continuously. Pull the entire bundle of conductors through the trunk line to the first junction box without stopping. Thirdly, identify conductors. As the conductors emerge from each junction box, identify them by their markers and route them to the appropriate devices. This eliminates the need to pre-cut wires, but requires careful labeling and organization. Method 3. Pull string method. Firstly, install a pull string. Before installing any conductors, pull a thin, strong string or cable through the entire trunk line. This pull string will serve as a guide for pulling the conductors. Secondly, tie conductors to the pull string. At the controller cabinet, securely tie the conductors to the pull string. Ensure the connection is strong enough to withstand the pulling force. Thirdly, pull conductors through. Pull the pull string from the opposite end of the trunk line to draw the conductors through the conduit system to the junction boxes. Fourthly, untie conductors. Once the conductors are pulled through, untie them from the pull string and route them to the respective devices in each junction box. To further enhance the wire pulling process, consider the following tips. Firstly, use conduit lubricant. Apply a generous amount of conduit lubricant to the conductors before pulling them through the conduit. This significantly reduces friction and makes the pull much easier. Secondly, pull slowly and steadily. Avoid jerking or yanking on the wires, as this can damage the insulation or even break the conductors. Maintain a slow and steady pulling motion. Thirdly, use a cable drum. Employ a cable drum or reel to manage the bundle of wires. This prevents tangles and keeps the wires organized during the pull. Fourthly, use colored tape or markers. If you have multiple runs of the same wire type, use different colored tape or markers to clearly identify each run. This prevents confusion and ensures correct connections. Fifthly, consider prefabricated wiring harnesses. For complex systems, consider using prefabricated wiring harnesses or cables. These harnesses are custom-made to your specifications and can save significant time and reduce the risk of wiring errors. When dealing with specific wire types, it's crucial to adhere to relevant electrical codes and standards. For instance, when using THHN or THWN-2 conductors, it's essential to know the properties and limitations. THHN stands for thermoplastic high heat resistant nylon coated. THHN is a type of building wire commonly used for electrical wiring in residential, commercial, and industrial applications. THHN wires are insulated with a tough, heat-resistant thermoplastic material and are covered with a nylon jacket for added protection against abrasion and chemicals. THWN-2 stands for thermoplastic heat and water-resistant nylon coated too. THWN-2 is another type of building wire similar to THHN, but with enhanced moisture resistance. The 2 in THWN-2 indicates that it is suitable for use in wet locations and has a higher temperature rating compared to standard THWN wire. Here are some key characteristics and considerations for using THHN and THWN-2 wires. Voltage rating. THHN and THWN-2 wires typically have a voltage rating of 600 volts, making them suitable for most general-purpose wiring applications. Temperature rating. THHN wire has a temperature rating of 90 degrees Celsius or 194 degrees Fahrenheit in dry locations and 75 degrees Celsius or 167 degrees Fahrenheit in wet locations. THWN-2 wire has a higher temperature rating, typically 90 degrees Celsius or 194 degrees Fahrenheit in both wet and dry locations. Applications. THHN and THWN-2 wires are commonly used for wiring in conduit, cable trays, and other raceways. They are suitable for use in both dry and wet locations, making them versatile for a wide range of applications. Code compliance. When using THHN and THWN-2 wires, it's essential to comply with the relevant electrical codes and standards, such as the National Electrical Code, NEC, or other local regulations. These codes provide guidelines for wire sizing, installation methods, and other safety requirements. Wire sizing. The appropriate wire size for a particular application depends on the ampacity or current carrying capacity required for the circuit. Refer to the NEC tables such as Table 310.15, B16 to determine the correct wire size based on the load and ambient temperature. Conduit fill. When installing THHN or THWN-2 wires in conduit, it's important to ensure that the conduit fill does not exceed the maximum allowable fill percentage specified in the NEC. Overfilling the conduit can make it difficult to pull the wires and can also reduce the ampacity of the conductors. Grounding. Proper grounding is essential for electrical safety. Ensure that the grounded conductor is correctly sized and installed according to the NEC requirements. Use appropriate grounding methods such as grounding bushings or grounding lock nuts to ensure a secure connection between the conduit and the equipment grounding conductor. Termination. When terminating THHN and THWN-2 wires, use appropriate connectors and terminals that are rated for the wire size and type. Ensure that the connections are tight and secure to prevent overheating and electrical faults. Protection. Protect THHN and THWN-2 wires from physical damage and abrasion during installation and operation. Use conduit, cable trays, or other protective measures to prevent damage to the insulation. Color coding. Use color-coded wires to identify different circuits and phases. This makes it easier to troubleshoot and maintain the electrical system. Common color codes include black for hot wires, white for neutral wires, and green for grounding wires. Inspection. After completing the wiring installation, thoroughly inspect the connections and wiring to ensure that everything is installed correctly and safely. Use a multimeter or other testing equipment to verify the continuity and installation resistance of the circuits. Documentation. Keep accurate records of the wiring installation, including wire sizes, circuit diagrams, and termination details. This information will be helpful for future maintenance and troubleshooting. When working with control and fire alarm systems, specific considerations apply due to the critical nature of these systems. Reliability. Control and fire alarm systems must be highly reliable to ensure proper operation in emergency situations. Use high-quality components and wiring methods to minimize the risk of failures. Redundancy. Consider incorporating redundancy into the system designed to provide backup power and communication pathways in case of failures. This can include using redundant power supplies, communication lines, and control modules. Supervision. Implement supervisory circuits to monitor the integrity of the wiring and components. Supervisory circuits can detect open circuits, short circuits, and other faults that could compromise the system's operation. Wiring methods. Use appropriate wiring methods, such as shielded cables or conduit, to protect the wiring from electromagnetic interference or physical damage. Separate power and signal wiring to minimize noise and interference. Grounding. Ensure proper grounding to minimize the risk of electrical noise and ground loops. Use dedicated grounding conductors and grounding electrodes to provide a low impedance path to ground. Testing. Thoroughly test the system after installation to verify that it is operating correctly. Test all inputs, outputs, and communication pathways to ensure that they are functioning as designed. Documentation. Maintain detailed documentation of the system design, wiring diagrams, and test results. This information will be helpful for future maintenance and troubleshooting. By following these guidelines and best practices, you can ensure that the wiring installation for control and fire alarm systems is safe, reliable, and compliant with relevant codes and standards. Remember to consult with qualified electrical professionals and engineers to ensure that the system design and installation meet the specific requirements of your application. When pulling wires, always consider the bend radius of the conductors to avoid damaging the insulation. The bend radius is the minimum radius that a wire or cable can be bent without causing damage to its insulation or conductors. Exceeding the minimum bend radius can result in kinking, cracking, or breaking of the insulation, which can lead to electrical shorts, ground faults, or even fire hazards. The minimum bend radius for a particular wire or cable is typically specified by the manufacturer and is based on the wire's construction, materials, and size. In general, larger wires and cables have larger minimum bend radii than smaller ones. The NEC provides guidelines for minimum bend radii in various sections depending on the type of wiring and installation method. For example, Section 300.34 covers the minimum bending radii for conductors and general wiring, while Section 334.24 addresses the minimum bending radii for non-metallic sheath cable. To determine the minimum bend radius for a specific wire or cable, consult the manufacturer's specifications or refer to the relevant NEC tables and sections. The minimum bend radius is typically expressed as a multiple of the wire or cable diameter. For example, a wire with a minimum bend radius of 6 times its diameter can be bent to a radius of 6 times the wire's diameter without causing damage. When installing wires and cables, it's important to avoid exceeding the minimum bend radius by using appropriate bending techniques and tools. Use conduit benders, cable benders, or other specialized tools to create smooth, gradual bends without kinking or damaging the insulation. When pulling wires through conduit or other raceways, be careful not to force the wires around sharp corners or obstacles. Use pulling elbows, sweeps, or other fittings to provide a smooth path for the wires and avoid exceeding the minimum bend radius. After completing the wiring installation, inspect the wires and cables for any signs of damage or kinking. If you find any areas where the minimum bend radius has been exceeded, correct the installation to prevent future problems. By following these guidelines and best practices, you can ensure that the wiring installation is safe, reliable, and compliant with relevant codes and standards. Remember to consult with qualified electrical professionals and engineers to ensure that the system design and installation meet the specific requirements of your application. Another critical aspect of wire pulling involves understanding and adhering to conduit fill requirements as specified by the NEC. Conduit fill refers to the percentage of the interior cross-sectional area of a conduit that is occupied by conductors. The NEC sets limits on conduit fill to prevent overheating of conductors, facilitate heat dissipation, and ensure that wires can be easily pulled and removed. Overfilling a conduit can lead to several problems. Firstly, reduced ampacity. When conductors are packed too tightly in a conduit, they cannot dissipate heat effectively. This can cause the conductors to overheat, which reduces their ampacity or current carrying capacity. Secondly, insulation damage. Overfilling a conduit can also damage the insulation of the conductors. The tight fit can cause abrasion and friction, which can wear away the insulation and expose the conductors to potential shorts or ground faults. Thirdly, difficult wire pulling. Overfilled conduits make it difficult to pull wires, especially when making bends or turns. This can increase the risk of damaging the conductors and can also make it difficult to remove or replace wires in the future. Fourthly, code violations. Exceeding the maximum allowable conduit fill is a violation of the NEC, which can result in fines or other penalties. The NEC specifies the maximum allowable conduit fill based on the type of conduit, the number of conductors, and the size of the conductors. The fill percentage is calculated as the total cross-sectional area of all conductors in a conduit divided by the interior cross-sectional area of the conduit, multiplied by 100. The NEC provides tables, such as Table 1 in Chapter 9, that list the dimensions and cross-sectional areas of various types of conduits and conductors. To determine the maximum number of conductors that can be installed in a particular conduit, follow these steps. Firstly, determine the type and size of the conduit. Identify the type of conduit being used, such as rigid metal conduit, RMC, electrical metallic tubing, EMT, or a flexible metal conduit, F&C, and determine its trade size. Secondly, determine the type and size of the conductors. Identify the type of conductors being used, such as THHN, THWN, or XHHW, and determine their size in American wire gauge, AUK. Thirdly, look up the cross-sectional area of the conduit and conductors. Refer to the NEC tables to find the interior cross-sectional area of the conduit and the cross-sectional area of each conductor. Fourthly, calculate the total cross-sectional area of the conductors. Multiply the cross-sectional area of each conductor by the number of conductors of that size in the conduit, and then add up the results to get the total cross-sectional area of all conductors. Fifthly, calculate the conduit fill percentage. Divide the total cross-sectional area of the conductors by the interior cross-sectional area of the conduit, and then multiply by 100 to get the conduit fill percentage. Sixthly, compare the conduit fill percentage to the allowable limit. Refer to the NEC to determine the maximum allowable conduit fill percentage for the type of conduit and the number of conductors. If the calculated conduit fill percentage exceeds the allowable limit, you must either increase the size of the conduit or reduce the number of conductors. In addition to the general conduit fill requirements, the NEC also includes specific requirements for certain types of installations. For example, Section 344.22 covers the conduit fill requirements for RMC, while Section 348.22 covers the conduit fill requirements for EMT. When pulling wires through a conduit, it's important to use proper techniques and tools to avoid damaging the conductors or the conduit. Use conduit lubricant to reduce friction and avoid pulling the wires too hard or too fast. If the wires are difficult to pull, consider using a wire pulling machine or a fish tape to help guide the wires through the conduit. After completing the wiring installation, inspect the conduit to ensure that it is not overfilled and that the wires are properly installed. If you find any problems, correct the installation to prevent future issues. By following these guidelines and best practices, you can ensure that the wiring installation is safe, reliable, and compliant with relevant codes and standards. Remember to consult with qualified electrical professionals and engineers to ensure that the system design and installation meet the specific requirements of your application.